Hi, everybody. Today, we're going to start with complexity theory. So remember that we have seen regular languages, we've seen context-free, then we went to study decidable languages and Turing machines, and now we go back a little bit, and we go to study P and NP. Let us begin with some motivation. Recall the language ATM, which is a language of pairs MW, where M is ATM and M accepts W. This language is undecidable, as we saw. However, what about a bounded version of ATM? Let's call it BTM. It's the language of pairs MW, where M is a Turing machine and M accepts W in at most 2 to the 500 steps. Is BTM undecidable? What do you think? No, BTM is decidable. Why? When we just run M on W for this many steps, done. Okay, just need to wait long enough. Okay, but is this practical? It's not. Well, let's throw in some numbers. With today's computers, you can maybe do an instruction every 10 to the minus 10 seconds. And people think there is some kind of physical limit that you will not be able to do an instruction in less than 10 to the, say, minus 43 seconds. Okay? So even if you reach this physical limit, to run M for through the 500 steps, it will always take you at least this many steps times the physical limit, which is much longer than 5 billion years. And that's the estimated lifespan of our sun. So the sun will die before you get the answer. So to run this machine for this many steps is impractical. And this is regardless of the hardware, the programming language, and so on. Doesn't matter if I'm using Java or Turing machine, it's still too much. Okay? So desirability is not really getting to the core of the question of which problems we can solve. Complexity aims to answer that question. Complexity theory studies which languages can be decided within a reasonable amount of time and which ones cannot. So how are we going to measure time? Well, we can think of time of a TM computation as the number of the steps that the machine makes. An important thing is here that we're going to count steps as a function of the input length of W. And this makes sense, okay? If I give you longer and longer inputs, you have to spend more and more time just to read the input. You need to spend the length of W steps just to read the input W. So the time will not be a fixed number like 17 or 2500, but it will be a function of the input length. For example, let's recall the Turing machine for A to the M, B to the M, C to the M. Okay. How did it work? On input W, you scan a tape and you cross off 1A, 1B, and 1C. If you don't find the symbols, you accept. If you don't find, if not all of them are found, you reject, or you also reject if they're in the wrong order, you continue. How long does this take? What do you think? How many steps will it take as a function of the input length? Well, let's do one by one. Part one takes 2 times the length of the input steps because you scan forward and backward. How many times are we going to repeat that? Well, every time we cross off 3 symbols, right? So we're going to repeat that at most length of the input divided by 3. We make 3 marks each time. So in total, the Turing machine runs for how many steps? Well, it would be at most 2w times 2 times length of w times length of w divided by 3, which is, let's say, 2/3 times the length of w square. Okay, so here we have seen a precise bound on the running time of this machine. Let's consider another example. Remember the machine for the language a to the 2 to the m, so the language of strings just made of a's, whose length is a power of 2. And on input w, if there's only one a, you accept, otherwise you're going to cross off every other a, and then you check if this number was odd or even, and you go back to 1. How long does this take? What do you think? Think about it. Well, part 2 takes length of w steps, because we come forward and back like before. How many times are we going to repeat this? This is an important thing. We repeat at most log the length of w times, because each time half of the remaining a's are crossed out. So in total, the Turing machine is going to run for how many steps? 2 times the length of w times log the length of w. Okay. So now we're ready for our definition of time. And there is some notation which is very common. We're going to use the letter n to stand for the input length of w. So if you have some function in mind, t, we're going to define by time t of n the set of languages that can be decided by a Turing machine that runs for at most t of n steps on every input of length n. For example, a to the m, b to the m, c to the m is in time 2/3 n square. Note how I use the letter n to indicate the input length. And the language a to the 2 to the m is in time 2n log n. How robust is this notion of time? Recall that for every language L, we mentioned earlier that L is decidable in Java if and only if L is decidable on a Turing machine. In terms of desirability, there is no difference between Java and Turing machines. Does anything like this hold for time? What do you think? Well, the time equivalence between Java and Turing machine and all other programming languages is not exact. In particular, there are languages that can be recognized in time n in Java, so you just do a pass on the input, but they require time at least n squared on a Turing machine. Okay, this comes from the fact that the Turing machine moves the head sequentially just by time squared, while Java can jump around in the memory. Surprisingly, the gap is not much bigger than that. There's a theorem that if you have a computation which runs in time t of n in Java, you can do that in time t of n to some power c on a Turing machine. And vice versa, any computation on a Turing machine that runs in time t of n can be done in time t of n to some power c in Java. Okay. So for example, if you have a computation, for example, time n in Java is how long on Turing machines? Will be time n to the c. And if you have time n squared in Java, there will be time n to the 2c. Okay, so you place this constant c here, goes in the exponent, you get time n to the 2c. And fairly small values of c are possible. We're shown like c equals to 3 suffices in most cases. One direction of this theorem is fairly easy, that's simulating Turing machines in Java. The other one is more complicated. You have to program Turing machine to simulate a Java program. But it's not too bad, and you will maintain the entire memory of the Java program on a tape, and every time the Java program has to access a location, the Turing machine will go back and forth on the tape to look for the corresponding item. So it's not terribly hard, but it's somewhat technical. Okay, now a key definition is that of P, what's called polynomial time. But you can also call this power time because it corresponds to time bounds, which are a power of the input length. So P is the union over C of time n to the C. So it's a time n, union time n square, union time n cube, and so on. And the nice thing of P is that this class is robust, is invariant under computational model. So P on Java is the same as P on TMs. So this is our notion of efficiency. It is as close as we get to model your laptop, if you have one. Okay, so P is our notion of efficient computation. You can be more precise. It makes a lot of sense to think of like, time n in Java for efficient, and this can be done, and there is some interesting theory in complexity which deals with that, but now we're just seeing the big picture, so we're going to just think of P. Also because most or all of what you have a program is in P. The previous example that we gave were all polynomial time or power time computation. They were all in P. So the algorithms class studies languages in P, and there you also distinguish between time, say, n square and n cube. It makes a huge difference if an algorithm runs in time n square or n cube. For this type of distinction, TMs are not fine enough, right? Because the gap between Java and TM is a power, it's like maybe n to n square. In this class, however, the main focus is what is not in P. Now, if that's what you're after, then it doesn't matter too much the distinction between n square and n cube. So we're not going to distinguish between n square and n cube, and we can work with Turing machines. So what languages are not in P? Can anyone think of a language which is not in P? ATM. Recall ATM, the language of pairs MW, where M is a Turing machine which accepts W, is even undesirable. So in particular, it's not in P. So despite intense research, ATM is essentially the only language that we can prove unconditionally to be outside of P. Sad face. However, there are many other languages which are believed to be not in P. For example, the set problem, which we're going to define soon, the factory integer problem, and so on. Among these, there is a class of interesting languages or problems which are called NP-complete. NP-complete problems include problems that people care about because they occur frequently in practice. And they have a nice feature, which we're going to see later, that if any of these problems is in P, then all of them are. So what we're going to do next, we're going to define several NP-complete problems, like SAT, click, subset sum, and we're going to prove polynomial time or power time reductions, which are implications of the form if click is in P, then also SAT is in P. If subset sum is in P, then SAT is in P. And we're going to define that A reduces to B in polynomial time if B in P implies A in P. Okay, so if you have an algorithm that runs in polynomial time for B, then you also have one for A. Okay, and we're going to call this implication a polynomial time reduction or power time reduction. This is conceptually like the implication which we saw earlier, that if L is decidable, then also ATM is decidable. The main difference is that before, earlier, we could obtain unconditional results because we know that ATM is undecidable. Okay? Now we don't know that. We're just going to use implications to link problems to prove that if one problem is easy, then the other one is easy as well. So in the next lectures, we are going to formally state these problems and we're going to prove the reductions. Bye now.